Hi guys, I trust that you're feeling well and great. Welcome to this tutorial on grade 10 mathematics, and in this lesson we'll be having a look at the number system. So the content for today is we'll have a look at the number system. What are the different types of numbers that we have? What is the need for the number system and how do we actually apply it? We're going to have a look at decimals, so the different types of decimals that you have. We're going to have a look at how to round off the decimals. We'll also look at how to convert decimals into fractions. We're then going to have a look at estimating surds. So this is cases whereby they say to you, for example, determine between which two integers the square root of 2 lies. So without any further ado, let's get straight into it. A number system is a collection of different types or groups of numbers. Now, this might not make sense at this point in time, but for some of you who are willing to do or who are planning to do IT, engineering, and the likes at university, you will notice that there's different types of numbers besides the ordinary numbers that we just use in everyday language. Some are used for counting, some are used for more complex manipulation of computers, some are used heavily in engineering, but we shall not get into details with all of those. What we are concerned about is the different properties that numbers have that we could use to group them. So the different types of numbers that you're going to be having a look at in grade 10 right through grade 12 are natural numbers, whole numbers, integers, rational numbers, irrational numbers, real numbers, as well as non-real numbers. Now let's have a look at the first set of numbers, or the first type of numbers. We've got natural numbers. What are natural numbers? Well, natural numbers are counting numbers. And natural numbers, take note of this, must always start from 1. Now, one way I like to think about this is, count the number of learners in your classroom. Where do you start counting from? You always start from the number 1. You will say, this is position 1, position 2, and that's how you continue counting. You do not start counting from 0. You do not start counting from a negative number. Do we start from 0? Nope. Do we reach a negative number? No, we don't. Do we have a decimal? No. For example, if you're counting the number of learners in your classroom, it would not make sense to say you've got, let's say, 37,5 learners. It does not make sense. It always has to be a natural number, no decimals. So the set of natural numbers, an example of the set of natural numbers, includes but is not limited to the following numbers. We've got 1, 2, 3, 4, etc. Now, when we say it includes but it is not limited to, notice the ellipsis here means that there are more numbers. So that should tell you that natural numbers have a smallest value. So the minimum natural number that you have, the smallest natural number that you have will always be 1. That's where we start counting from. We do not start counting from below 1. I hope that this makes sense. We now come to whole numbers. Whole numbers are just like natural numbers. The only difference is that whole numbers start from the number 0. All natural numbers are whole numbers, but not all whole numbers are natural numbers. Let's repeat that. All natural numbers are whole numbers, but not all whole numbers are natural numbers. I'll give you an example to demonstrate this. All girls are humans, but not all humans are girls. What does this mean? For us to have a number being natural, it has to start from 1, should not be a decimal, should not be negative. But now, whole numbers are the same as natural numbers, exactly the same. The only difference is that we are adding the number 0. I hope that the distinction makes sense. Whole numbers can also not be negative, they cannot be decimals, but they can be 0. So basically what we're saying here is, just like natural numbers, whole numbers cannot be negative, whole numbers cannot have decimals, but whole numbers can have 0. So the only way to distinguish between a set of natural numbers and a set of whole numbers is to check for the presence of the number 0. If we have the number 0, the numbers are whole numbers. If there is no number 0, there is no negative number, there is no decimal, then we have natural numbers. So here we are, we've got a set of whole numbers which start from 0 and go up to infinity. Just like with natural numbers, we've got a minimum when it comes to whole numbers. The minimum for whole numbers will always be the number 0. That should tell you if we have numbers less than 0, we're no longer looking at whole numbers. We're looking at something else. I hope that this makes sense, and I hope that you guys are learning and enjoying the content. If you are, please give us a thumbs up. Please subscribe to the channel, and please hit the bell icon so that you can receive a notification every time when we upload new videos. Also, please don't be selfish. Please share this video with other people so that they can benefit from the same knowledge that you're benefiting from right now. Alright, now we get into integers. Integers are positive and negative numbers. So for example, if I have a look at negative 16, this would be an example of an integer. Why? Because it has a negative sign. If I look at the number 4, let's talk about this. We can write the number 4 as plus 4. So this is an integer. But now we also have 4 being part of our natural numbers. We also have 4 being part of whole numbers because 4 is a counting number. So therefore we can see here that a single number can belong to more than one group of numbers. I hope that this makes sense. Integers cannot be decimals. Integers can be negative, as we see here. Integers can also include the number 0. All whole numbers are integers. So that should tell us that natural numbers are also integers. So now, the set of integers that we have includes, for example, negative 3, negative 2, negative 1, 0, 1, 2, 3, etc. In this case, we do not have a minimum value for integers. I can say my minimum value for integers would be negative infinity. Because any negative number, does not matter how small or big, forms part of integers. I can also say my maximum number here would be positive infinity. What does this mean? Any number, doesn't matter how big or small, as long as it's positive, it is still an integer. I hope that this makes sense. We have rational numbers. Now, a rational number, this is a number which can be expressed as a fraction, a over b. We are saying that b cannot be equals to 0. By the way, why are we saying b cannot be equals to 0? We have learned that any number divided by 0 gives you undefined. So what we are saying is the denominator of this fraction that we have cannot be 0. We are also saying that a and b are elements of integers. So when you read this, you say a and b are elements of integers, meaning my numerator and my denominator must be integers. So if I have, for example, negative 3, this is a rational number because I can write this as a fraction to be negative 3 divided by 1. My numerator is an integer, my denominator is an integer, therefore this is a rational number. I can have 6 over 4. Notice it's in the form of a fraction. This is an integer, this is an integer, so that's good to go. This is still a rational number. But if I have something like the square root of 3 over 2, this is not a rational number. Why? The square root of 3, as you will see later on, this is not an integer. Remember, we said integers, we do not include decimals. Now, if you press the square root of 3 on your calculator, you will get a number which has many numbers after the comma. This indicates to you that the square root of 3 is not an integer because it's a decimal. Please take note of this. So we said rational numbers can be written as fractions. Once again, the numerator must be an integer, the denominator must be an integer. Because as we saw earlier, even if we can have something like 16 divided by the square root of 4, well, I can say this is 16 divided by the square root of 4, this is going to give me 2. Already this is a fraction, this is an integer, 2 is an integer, therefore this is a rational number. However, if I have 5 divided by the square root of 7, the square root of 7 is a decimal. because this is a decimal, whoops, this is a decimal, this whole fraction does not count as a rational number anymore. Please take note of this. Integers are rational numbers. It means whole numbers are rational numbers. Natural numbers are also natural numbers. Sorry, natural numbers are also rational numbers. If I take 0, how is 0 a rational number? How can I write 0 as a fraction? I can say 0 divided by anything. For example, 0 divided by 3 will give me 0. 0 divided by 12, it still gives me 0. So as long as my numerator is 0, then I will always get an answer of 0. By the way, my numerators in this case, these are all integers. My denominators in this case, these are all integers. Therefore, these fractions that I've written here, if I could just go back, these fractions are examples of rational numbers. We have a new set of words here. Recurring and terminating decimals are rational numbers. Notice, we are talking about decimals. Now, what is a terminating decimal? This is a decimal number that can end after a certain number of digits. Notice 0,5, there's nothing more after the 5. That's a terminating decimal. 0,0625, there's nothing else after the 5. It's a terminating decimal because it stops. It ends. 1,337, there's nothing after the 7. The decimal stops. Therefore, this is an example of a terminating decimal. Now, we are saying that terminating decimals are also rational numbers. It means we can write terminating decimals as fractions. And we'll actually have a look at this a little bit later on. Recurring decimals are decimals with repeating digits, and they do not end. So for example, 0,33333, the ellipsis indicates that the pattern continues to infinity. Therefore, this is a recurring decimal. Please take note. We are not saying that recurring decimals are numbers that do not end. No. Recurring decimals are numbers that do not end, but there is a repetition of digits. The second example, 1,656565, the ellipsis indicates that the decimal doesn't end. But at the same time, we can see that if we continue, there'll be a pattern of 65, 65, 65, 65, up to infinity. This is an example of a recurring decimal. Since recurring decimals are rational numbers, we can also write recurring decimals as fractions. We'll have a look at this a little later on. We've got irrational numbers now. Irrational numbers are numbers which cannot be written as a fraction, with both numerator and denominators being integers. As I've mentioned to you earlier, the square root of 3 over 2 is an example of an irrational number. Why? Because my denominator is an integer, but my numerator is not an integer. Therefore, inasmuch as this can be written as a fraction, because my numerator and denominator are not both integers, we cannot count this to be rational numbers. We say they are irrational numbers. Notice that the sign for irrational numbers has the little ellipsis here to indicate that it's, the little apostrophe, to indicate that it is not rational. I hope this makes sense. Non-terminating and non-recurring decimals are irrational numbers. So now we are saying that the decimals do not end. There's also no repetition of numbers after the decimal point. Therefore, we can say these are irrational. Here we have examples. The number pi, we know pi is 3,141, etc. If you look at this number here, 12,548, you will notice that the digits are not repeating after the comma. But at the same time, the ellipsis indicates that they continue to infinity. This is an example of an irrational number. Negative 0,157, etc. Numbers do not repeat. There's no pattern. The numbers also do not end, therefore this is an irrational number. Life is great. I hope that this makes sense. We have real numbers. All rational and irrational numbers are real numbers. So what are we saying? Natural numbers, whole numbers, integers, rational and irrational numbers are real numbers. One way to think about this is any number that you can think of is a real number. For as long as you do not get undefined when you're working with the number or when you're using it in a calculation, that number is said to be a real number. Then we've got non-real numbers. Non-real numbers, these are numbers where we've got division by 0. Remember, if I say 3 divided by 0, I'm going to get math error. So this is an example of a non-real number. The square root of a negative number you've been taught does not exist. So the square root of negative 16, if you press this on your calculator, you're going to get a math error. These group of numbers are what we call non-real numbers. So these are the ones that you typically think of as being undefined, as I mentioned, when you're using them on a calculator. Here we've got some more examples of non-real numbers. This is supposed to say non-real numbers. It's a typing error. So we've got 6 divided by 0, square root of negative 4, square root of negative 16, etc. Alright, enough said about the number system. Now, remember earlier when we spoke about rational numbers, we said we've got terminating and recurring decimals, which can be written as fractions. Now we want to get into writing these decimals as fractions. So we said we looked at two types of decimals, our terminating and recurring decimals. We mentioned earlier in our presentation, terminating and recurring decimals are rational numbers. Now we want to know how we can convert them into a fraction with an integer numerator and an integer denominator. So how do we convert terminating decimals into fractions? A terminating decimal has an integer part. So the integer part, this is a number before the comma, and a fractional part, this is all of the numbers after the comma. If I look at 3,64, 3,64, the 3, this is what we call the integer part. Then everything after the comma, this is what we call the fractional part. So this is the fractional part. Now, you might be thinking, why do I need to know that? You'll see in a second. Each number after the comma can be written as a fraction with a denominator of increasing powers of 10. Does this make sense? No. Mr. Brown, what are you saying? Let me show you what I'm talking about. If I take the same 3,64, let's say 5,7. Let's look at the fractional part, meaning the part after the comma. I could say 6 over 10 to the power 1, if you want to think of it that way, plus 4 over 100, which is 10 to the power 2, plus 5 over 1000, which is 10 to the power 3, plus 7 over 10,000, which is 10 to the power 4. So what we're saying is, as we go that way, the powers of 10 increase. 10 to the power 1, 10 to the power 2, 10 to the power 3, 10 to the power 4. Let's look at a quick example. Another example. If I have, let's say, 0,25, simple example. If I look at the fractional part, I can write this as 2 over 10 plus 5 over 100. Please take note of this. We can add the integer part and the fractions of all of the digits after the comma. So again, if I look at, let's say, 16,47, I could say this is 16, our integer part. Then I'm going to add the fractions of the fractional part. We said the 4 here is going to be 4 over 10 plus 7 over 100. I hope that this makes sense. This is exactly how we are going to convert our terminating decimals into fractions. Enough said, let's look at a practical example. Alright, convert the following terminating decimals into fractions. We've got 0,23. Let's head over to our writing pad and let's have a look at how we would do such a question. So, we are given 0,23. We said, let's just label this quickly. The 0, we said this is our integer part. And then we said the 0.23, this is our fractional part. So how do we simplify this? We take our integer part, in fact, let me use a different color. We take the integer part plus, this is a 2, so this is going to be 2 over 10, increasing powers of 10 on our denominators, plus 3 over 100. You can go ahead and type this into your scientific calculator because you guys can't survive without a scientific calculator, right? I assume that by now you are familiar with how to use your scientific calculator. So if you simplify this, you're going to get a fraction of 23 over 100. This is a terrible line. Let me try this again. This is 23 divided by 100. To check if your answer is correct, you can press 23 over 100 on your calculator. This is just for checking. You don't have to do this when answering the question. If you press 23 over 100 on your calculator, it takes you back to the decimal that we had initially. So in other words, what are we saying? We are saying 0,23 as a fraction is 23 over 100. This is a rational number. Why? Because 23 is an integer, 100 is an integer. We are able to write a numerator and a denominator with integers. Therefore, we are done. Life is great. 0,23 is 23 over 100 as a fraction, ladies and gentlemen. I love this. Let's move on to the next example. So in the next example, we've got 6,45. Let's go back to our writing pad. Let's move down to get some room. So we've got 6,45. Remember what we said. Number before the comma, this is the integer part. Numbers after the comma, this is our fractional part. So how do we convert this? We say, okay, 6,45 is, take the integer part as it is. Then increasing powers of 10 on our denominators. So 4 over 10 plus 5 over 100. Let's see what this is going to give us. If you type this into your scientific calculator, which by now you have with you and you are enjoying the benefits of having a scientific calculator, you are going to get your answer is 129 over 20. Once again, if you press 129 over 20 on your calculator for testing purposes to check if your answer is correct, once again you're going to end up with 6,45. Now let's talk about this fraction. 129, that's an integer. 20 is an integer. Both the numerators and the denominators are integers, the numerator and the denominator. Both of them are integers. Therefore, 6,45, we've written it as a rational number. We've written it as a fraction, and therefore it's a rational number. Wonderful. All right, we've got 0,0625. Let's go back to the writing pad and try this one out. So let's just make some room here. 0,0625. Once again, let's start by labeling the fraction. This is our integer part. Then the 0,0625, this is our fractional part. So We proceed by first writing our integer part, and then we write the fractional part. So 0 over 10 plus 6 over 100 plus 2 over 1000. Notice that we keep on adding a 0 to our denominators as we move to the left. Sorry, as we move to the right. Plus 5 over 10,000. Now we can go ahead and press this on our scientific calculator to see what it gives us. Notice that despite the fact that we have a 0 here, we still need to include it. If you decided to start with 6 over 10, that's wrong, because the 6 comes after the 0. So we need to make sure that we respect the order in which our decimal values appear as. Otherwise, if you don't respect the order, you're going to end up with an answer which is going to be very much incorrect. So, after simplifying this, we get an answer of 1 over 16. If you press 1 over 16 on your calculator, once again, you're going to get 0.0625. We said 1 is an integer, 16 is an integer. We've got an integer over an integer, therefore, this is a rational number. We are done. Let's look at the next question. 8,67. Back to the writing pad. 8,67 is great. So, 8,67. Let's label. This is the integer part. Then, the 0.67, this is our fractional part. What I'd like you to do is to pause the video, try this out on your own, and then play the video again and see if we have the same answers. See if your working would match what I'm going to do. So, pause the video right now and try it out. Alright, assuming that you actually did pause the video and try it out, you know that we have to take the integer part as it is. Then we say 6 over 10 plus 7 over 100. And now you can go ahead, press this on your calculator and see what answer we are going to get. We are going to get an answer here of 867 divided by 100. Brilliant. Let's move on to the next question. 1,245. Let's go back and write 1,245. So let's make some room. Okay, you know what? New sheet of paper. A new sheet of paper right there. So our question was 1,245. This time around, I'm not going to do the labeling because, like I said, in your exam, it's not necessary for you to do the labeling. I just prefer that you do the labeling so that you know more or less where to go from here. So I'm going to say 1, my integer part, plus 2 over 10, the fractional part, plus 4 over 100, still the fractional part, plus 5 over 1000, still the fractional part. Go to scientific calculator, you know, the one you can't live without. Press what you have right now on scientific calculator. This is supposed to be 5 over 1000. After pressing this on your scientific calculator, you will get something like 249 all over 200. Wonderful, brilliant. Life is great. Now let's move on to the last question, 9,7784. So writing pad, let's scroll down, 9,7784. Now we know, take the 9 as it is, fractional part over 10, fractional part over 100, fractional part over 1000, fractional part over 10,000. Remember, we're talking about increasing powers of 10 on our denominator. So go to scientific calculator, the one you cannot live without. Type this into scientific calculator, the one you cannot live without. Let's see what our answer is going to be if I do a quick calculation. I'm actually going to get something like, this is 12,223 all over 1,250. Wonderful, brilliant, life is great. I hope that you guys now understand how to convert terminating decimals into fractions. If you don't understand, or if I'm moving too fast, or you're not clear on anything, please do go to the comment section and let us know. Let me know how you feel about the content that I've just covered. Maybe that I made a mistake, or you feel like I'm moving too fast. I'll re-upload the video if I have to, or I'll slow down in the next video. Alright, let's move on. Now that we know how to convert terminating decimals, we also need to find out how to convert recurring decimals into fractions. Because remember, we said both terminating and recurring fractions, both terminating and recurring decimals, are rational numbers. Now notice that recurring decimals have an infinite number of repeating digits after the comma. So we cannot use the same strategy that we did right now. To convert a recurring decimal into a fraction, we need to assign a variable to that recurring decimal. So let's say I have something like 0,6 recurring. I could say, let me make this x. I need to multiply the expression by a power of 10. Now you'll see what I mean in the next set of examples. We subtract the first expression from the second expression. We simplify the last expression. So let's have a look at this. This question wants us to convert our recurring decimals into the form a over b, meaning we need to convert them into rational numbers. We've got 1,666 recurring. Let's go to our writing pad. And for the sake of clearing confusion, I'm going to write this on a new sheet. So I have 1,666 recurring. I can write this as 1,6666 with an ellipsis. Now, the first step is I need to assign a variable to this. I'm going to say x is equals to 1,666 recurring. The next step is I need to multiply this by a power of 10. Ask yourself this question: how many digits are repeating? We only have one digit which is repeating. That's the 6. So as a result, what I then need to do is I need to multiply this whole expression by 10. Notice that there's 1 0 after the 1 because there's only one digit that repeats. If I multiply this by 10, I'm going to get 10x is equals to 1,666 times 10 is going to give me 16,666. Now I need to subtract. So I'm going to take my first equation, x is equals to 1,666. This is supposed to have ellipsis. This is supposed to have ellipsis. Then when I get to this point, what I want to do is I would like to subtract the 2. So let me have my division line there, which is a bit terrible. So there we are. We are going to subtract this. I put my minus sign right there. Now, remember, 10x minus x is going to give us, let me use black. 10x minus x is going to give us 9x. Now, 16 minus 1 is going to give us 15. We're going to remain with comma 0 because all of the 6's will subtract and we remain with nothing. Now I can say 9x is the same as 15 because 15 comma 0 is just anonymous to saying, sorry, it's just synonymous to saying it's just 15. We don't need to write the comma 0. The next step is I'm going to divide both sides by 9 because I want to solve for x. This is going to cancel this. X is equals to 15 over 9. If you go to your scientific calculator and you press 15,9, you are going to get an answer of 1,666 recurring. Now you don't have to do this. I'm just saying to you, if you want to check your answer, you can type this fraction into the calculator. It gives you exactly the same decimal that we started off with. Therefore, 15/9 is correct. I hope that this made sense. So, let's move on to the next question. In our next question, we've got 24,454545. I think you can see the pattern here. Let's go back to our writing pad. So what we have here is, first of all, black color, 24, let's see, what did we have there? 45, 45, 45, etc. Now, I'm going to assign this to a variable. X is equals to 24, 45, 45, 45, recurring. The next step says I need to multiply by a power of 10. Now ask yourself, how many digits are repeating after the comma? 4 and 5, there are 2 digits repeating after the comma. So I need to multiply this by a power of 10 that has 2 digits after the 1. I need to multiply this by 100. If I multiply this by 100, I'm going to get 100x is equals to 2445,45. Next, I am going to put the original expression here. So 4545. And what I'm supposed to do here is I need to subtract the 2. So 100x minus x, there's a minus here. This is going to give me 99x. Then 2445 minus 24. This is going to give me 2421, 0, because the 454545 will subtract. I can say 99x is equals to 2421. Divide by 99, divide by 99. So let's see. This is going to cancel that. X is going to be equals to 24. Whoops, a little mistake here. X as a fraction is going to be 2421 over 99. Now, if you simplify this, you're going to get 269 over 11. And basically what I said was, how many times does 9 go into 99? It goes 11 times. How many times does 9 go into 2429? Sorry, 2421. It goes 269 times. If you press 269 over 11 on your calculator, you will get 24, 45, 45, 45 recurring. What we have here is exactly the same as the decimal we started off with. So indeed, 24,45 recurring as a fraction is 269 over 11. Wonderful. Life is great. Maths is easy all of a sudden. Let's look at the next question. We've got 0,007 recurring. Notice the little dot here at the top indicates that the fraction is recurring. So let's go back to our writing pad and let's have a look at this. So we've got 0, wrong color. This is 0,007 recurring. If I write this out in full, this is going to be 0,00777, etc. So here, x is going to be equals to 0,00777. We said the next step is we need to multiply by a power of 10. Now, you might be saying, okay, in the previous question, we said how many digits are repeating. Looking at this, we've got repetition of the zeros and repetition of the sevens. Let's ask ourselves, how many times does the comma have to move for us to have a whole number? For us to have a whole number before the comma. So the comma has to move 1, 2, 3 times. The comma moves 3 times. Because the comma moves 3 times, I need to multiply by a number, a power of 10 that has 3 zeros after the comma. In this case, it's 1,000. So, when we have a look at this, we could say, okay, after multiplying out, I'm going to get 1000x is equals to 7,777. Let's put our original expression here and let's subtract. Whoops. This is going to be 0,00777. And now we can go ahead and divide this. Sorry, subtract this. So I'm going to put my subtraction right there. This is going to be 999x is equals to. Let's see. So what we will end up with here is a little bit of a different scenario. We're going to remain with 7 there. And notice something. We still have 7 minus 0. That's still going to give us 7. And 7 minus 0 is 7. Then we remain with the zeros. I really don't like how this is looking like, but let's work with it. So the next step would obviously be to divide by, let's see, we could go ahead and divide this by 999, divide this by 999, and what we are going to get here is, we get x is equals to 7 over 900. There we are. Life is great. If you press 7 over 900 on your calculator, you will get something like 7,777 times 10 to the power minus 3. Now this 10 to the power minus 3, let's think of it this way. Because the exponent is negative, you will remember from grade 9 when you were converting your exponential form into scientific notation and scientific notation into exponential form, that this negative indicates that there is a 0 comma. Then after 3 spaces, or let me say at position 3 after the comma, that's where we have the first 7. So that's going to be 1, 2, 3. And then the repetition of the 7s. That's exactly what we have in our original expression. The only trick here was to be able to convert our exponential form into a decimal form. Alright, the next section that we're looking at here would be rounding off decimals. So what is rounding off? It basically allows us to focus only on a certain number of digits after the comma in a decimal. Now this is usually the case with irrational numbers, but can also be terminating and recurring decimals. So basically if I have something like 3,1412583 for example, let's say I only want to focus on the first 2 digits, or I only want 2 digits after the comma. That's when I employ rounding off. So rounding off makes an irrational number seem to be rational, but it does not make it rational. How do we go about rounding off decimals? We count the number of digits after the comma that the question wants us to do. We put a line after the last digit that we counted. We look at the number after the line, and if that number is greater than or equals to 5, we add a 1 to the number before the line. If the number is less than 5, we do not do anything to the number before the line. Now there's a lot that was said here. Let's look at a practical example. So here we've got some numbers that we need to round off to 3 decimal places. Let's go to the writing pad and let's have a look at this. So here we are. The number that we have here is 12, let's see. This is 459 765 789. And we are asked to round this off to 3 decimal places. Now in this case, I'm not so much interested in whether this is a terminating or recurring decimal. I just need to round off. So the first thing we said is we need to put a line after the first 3 decimals. Sorry, after the first 3 digits. So 1, 2, 3. I need to put a line here. Then I look at this number after the line. It's a 7. Because this number is bigger than 5, I need to come here and I need to add a 1. So now what's going to happen is the 9 plus 1 is 10. So this is going to change into being a 0. Because we changed this to a 0, we need to add a 1 to the 5. So we're going to have 12,460. Now, why did I include the 0? Because the question says we need to have 3 decimal places. So there we are. We could have just said 12,46. But because this question strictly said we need to have 3 decimal places, we need to make sure that we've got 3 digits after the comma. I hope this makes sense. Let's look at the next question. So in our next question, we've got negative 1,66, 142, 121. Let's go write this down. So we've got negative 166, let's see. This is 142, 121. And the question says that we need to round this off to 2 decimal places. Once again, what I'm going to do is I need to count 2 digits. Put a line here. I look at the number after the line. This is a 2. This number is less than 5, so I don't do anything to the number before the line. This is just going to be negative 166, 14. There we are. 2 decimal places. Done. Next question. So I've got a very interesting number here, 0,215457896545599. I'm supposed to round this off to 5 decimal places. So I'm just going to write this on the sheet quickly, then we can have a look at it. So this is going to be 0,21545789654. 599, and we're asked to round this off to 5 decimal places. Now let's go to the writing pad after I've copied it down and let's check. So let's count the number of digits. We're supposed to count 5 digits. 1, 2, 3, 4, 5. Put a line right there. When I look at the number after the line, it's a 7. It's greater than 5, so I come here and I'm going to add a 1. This is going to give me 0,21546. We've got 5 digits after the comma. We are done. Life is great. The last question, 14,999,747. Let's go back to our writing pad. So we've got 14,999. Let's see, 747. We are told that this must be rounded off to 3 decimal places. Now let's see what's going to happen. We count 1, 2, 3, put a line. The number after the line is 7, so I need to come here and I need to add 1. If I add 1, 9 plus 1 is 10, so the 9 changes to 0, but now I need to add another 1 here. 9 plus 1 is 10, this changes to 0, I need to add another 1 here. 9 plus 1 is 10, this changes to 0, I need to add a 1 to the 14, it becomes 15. So this is going to give me 15,000. We could have just written 15, but the question strictly asked for 3 decimal places, therefore we need to adhere to the question and stick to 3 decimal places. I hope that this makes sense. And that's rounding off in short, ladies and gentlemen. Let's do our last section for this, which is estimating surds. So surds are numbers which are written underneath the square root sign. These numbers cannot be written as rational numbers. So in other words, we're talking about irrational numbers. The question will ask you to estimate between which 2 integers a surd lies. You need to write down a list of perfect squares or perfect cubes. Remember, perfect square is a number that if you find the square root of that number, you get a rational number. Perfect cube is a number such that when you find the cube root of that number, you get a rational number. So you need to determine between which two perfect squares or perfect cubes the number underneath the square root sign lies. You need to find the cube root or the square root of those two numbers, and then the surd will lie between the square root or cube root of the two numbers. Let's look at a practical example, the cube root of 38. And in our writing pad, let's go to a new sheet of paper. The question we were given is the cube root of 38. I can write this. First thing is I need to write a number, a set of perfect cubes. Because it's a cube root, I need to have perfect cubes. My perfect cubes, 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64. This should be enough. Notice 38 is between which two perfect cubes? 27 and 64. So let me put the 27 there, let me put the 64 there. This is the cube root of 38. I need to find the cube root of 64. I need to find the cube root of 27. Cube root of 27 is 3. Cube root of 64 is 4. Therefore, I could say the cube root of 38 lies between 3 and 4. There we have it. Life is great. Let's look at the next question. So next, we're looking at the square root of 44. Now we're dealing with the square root. So let's write down the question. We're looking at the square root of 44. Because this is a square root, let me write a list of perfect squares. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49. This should be enough. Now 44 is between 36 and 49. So I could say square root of 36 is less than the square root of 44, which is less than the square root of 49. So the square root of 36 is 6. This is less than the square root of 44, which is less than the square root of 49, which is 7. I could say, therefore, square root of 44 lies between 6 and 7. There we have it. Life is great. The next question, the square root of 13. So let's open a new sheet of paper here. And let's see, we've got the square root of 13. Square root, so let me put perfect squares. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. Let me take it like this. 13 is between 9 and 16. So let me put square root of 9 is less than square root of 13, which is less than square root of 16. Square root of 9 is 3. Square root of 13 is square root of 13. Square root of 16 is 4. Therefore, square root of 13 lies between 3 and 4. Brilliant. All right, let's look at our last question for this presentation, the cube root of 84. So, we're looking at a cube root here. Cube root of 84. I can say, okay, the cube root of 84, once again, cube root, I need to look at perfect cubes. All right, since we're looking at a perfect cube here, a cube root, we need to look at perfect cubes. So up here, 1 cubed is 1, 2 cubed is 8, 3 cubed is 27. Let's see, 4 cubed, that's going to give me 64. And then 5 cubed, this is going to give me 125. Now I can see 84 is between 64 and 125. So I'm going to say the cube root of 64 is less than the cube root of 84, which is less than the cube root of 125. The cube root of 64, this is going to give us 8. Sorry, this is 4. The cube root of 84 is just the cube root of 84. The cube root of 125 is 5. Therefore, the cube root of 84 lies between 4 and 5. Wonderful. I hope that this makes sense to you guys, and I hope that you did enjoy the video. If you enjoyed it, please give us a thumbs up. Please subscribe to the channel, turn on the notifications so that you'll receive an update every time we upload a new video. Until then, thank you guys for joining us. Enjoy the rest of the day. Please remember to share this video with others so that they can benefit from the knowledge that you're benefiting from. And I'll see you in the next one. Ciao.